Okay, so normally, you guys, this is actually going to be pretty quick today because normally when we're talking about thermodynamics, we are actually talking about not just enthalpy, but like when we refer to thermodynamics, we're actually normally referring to enthalpy, of course, delta H, also entropy or disorder, delta S, and free energy, delta G. These two things, delta H and delta S, and of course, temperature, those three factors all playing a role in determining whether or not a reaction is spontaneous or not. Okay, so the reason why we're only going to have to review enthalpy for this review session is because of your shortened year. So normally when you take a thermodynamics course in college or on a normal AP exam, we would also incorporate everything that we learned about entropy and free energy, but they are omitting those from the AP exam this year. So we only have to talk about enthalpy. But please do remember that, like, in terms of determining spontaneity, I do want you to have like a full understanding of chemistry. In terms of understanding whether or not a reaction is spontaneous, it does not just depend on heat, of course. It also depends on order and disorder and temperature. Okay, so with that being said, let's review the heat aspect of energy change in reactions. And it's obviously all sort of comes back to and starts with the first law of thermodynamics, which says that energy is conserved. So like if a reaction is releasing energy, it's going somewhere, it's doing something. And when we're talking about energy, when we're talking about energy change in reactions, we're talking about two things: the ability to transfer heat and do work. Okay, so Q is, of course, the heat transfer involved in a reaction, and W is the work being done by that reaction. Now, in physics, you think about work as like, pushing something across a surface, like a car driving down the road or like a ball rolling down a hill. In chemistry, when we're talking about work, we're talking about pressure volume work. So pressure times the change in the volume of a system. So in other words, like if you have a reaction that's taking place inside of a piston, and this reaction produces lots of gas, like so if we increase moles of gas, this volume is going to increase. And this volume increasing is work being done by the system on the surroundings. Okay, so when we're talking about heat transfer and work being done, the signs of Q and the signs of W are very important. Okay, so when you have the system doing work on the surroundings, like with an increase in volume, this would be a negative W. This is work done by the system on the surroundings. And if the reverse was true, like if you had a reaction that took place inside of here and produced fewer moles of gas, the atmospheric pressure is going to push that piston down. Oh, there's Samantha. Hi, Samantha. So this would be a positive W, where the work is done by the surroundings on the system. Okay, so the signs matter. It's just showing the direction that the work is being done, either by the system on the surroundings or the surroundings on the system. We have to pay attention to the sign conventions for Q as well. So if we have a reaction that's taking place that is exothermic, where the reaction is releasing heat out into the environment, that would be a negative Q. where the heat is leaving the reaction and going out into the surroundings. And if we had the opposite of that, where the reaction is absorbing heat, endothermic, you would have a positive Q. So this is the way that energy is transferred, either by a transfer of heat or by work being done. And the type of work that gets done in chemistry is what we call pressure volume work, where the creation of moles of gas or the reaction that makes fewer moles of gas will result in a change in volume when you have a container that can change volume. If the container cannot change volume, then you're going to end up with changes in pressure. Okay, so we're gonna sort of abandon the work conversation here for a little bit, and we're just gonna look at heat. We're gonna look at heats of reaction. So technically, Q and delta H are not the exact same thing. Okay, so like when you go to college and you take 2 years of thermodynamics in your mechanical engineering classes, you're gonna find out that heat and enthalpy are not exactly the same. For our purposes, the heat of a reaction or the enthalpy of a reaction is the same as Q. Okay,
it's a question. Really
it's
quick.
the same as heat. Yeah, go ahead.
What did you draw in the boxes?
That's
endo and exo. Is that just like the?
That's my reaction, Shreya. Is that Shreya?
Okay. Okay.
That's my blah, 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 reaction taking place.
Okay, just checking. Thank you.
Yeah, that's my reaction. I'm silly. Yeah, that's a bunch of nonsense, isn't it? Sure, you've seen me do that diagram before. You know that a random little scribble inside of a box is a reaction.
Okay, for some reason it was looking like a G or something like that, so like I was just checking.
Yeah, it's the reaction. Thank you. Thank you for clarifying for those who have not seen my bad handwriting and weird lectures before. Okay, so technically delta H's or heats of reactions are equal to Q at constant pressure. Okay, so just keep that in mind for college. Not really important for right now. Like when we're talking about the delta H of a reaction, we're talking about how much heat was absorbed or released. Okay, so they can be equivalent things for us for right now, but technically it's only true at constant pressure. Okay, so here are two different potential energy diagrams representing what I was talking about above, being endo and exothermic reactions. So when you have an exothermic reaction like we have here on the left, you're going to have a negative delta H of your reaction because your products end up with less energy than your reactants. So how did that happen? By a release of energy. And over here on the right, we have, of course, our potential energy diagram showing our products with more energy than our reactants. Where did they get that energy from? They had to have absorbed it. So a positive delta H. And of course, don't forget all of the other important things that you can understand from these diagrams being, activation energy, the energy needed to get those reactants up into that transition state. Remember, these diagrams can have two steps, right? So you can have two activation energies and a rate limiting step based on your slow step. This is all the stuff we talked about last week when we were reviewing kinetics. But for now, all we care about in this review is whether your delta H's are positive or negative. How much heat are we going to get from this reaction, or how much heat are we going to need to be able to put in to get this reaction to occur? And of course, why do we care? Well, like we care about whether or not reactions are absorbing or releasing heat because like that determines whether, like what sorts of conditions we need to have in order to make that reaction take place. If we have to put in a certain amount of energy, we need to know how much energy that is. Also, we can do stuff with the energy that's released from reactions, from hot packs to turning water into steam to turn our turbines. So, the heats of reaction are very important in terms of the reaction's usefulness to us. And so there are a bunch of different ways to measure it. And so that's what we're going to talk about next. How do we actually, it's nice that it's on this diagram, but like how do scientists actually figure out the magnitude of this number? Bunch of different ways to figure it out. So how do we measure heats of reaction? One way to measure heats of reaction is by straight up measuring it in the lab. And the laboratory method that we use to measure heats of reaction is calorimetry. calorimetry. And we're going to talk much more about this in detail here in a few minutes. But lab method, calorimetry, you guys should automatically go to your Q equals MC delta T equation. Again, we'll look at the details of this here a little bit later on. Now, remember, the amount of heat you get in a calorimetry reaction is, or a calorimetry measurement, I should say, is going to depend on how much stuff you reacted. Okay, so like if I do the reaction with like 50 mils of limiting reactant, like let's say I'm doing like sodium hydroxide and hydrochloric acid. And so I use like 50 mils of limiting reactant, but Shreya uses 100 mils of limiting reactant. She's going to get twice as much heat as I'm going to get in terms of just like an absolute magnitude of that number. So Q, when we're talking about the heat evolved in a reaction in the lab, that value is an extensive property. Like it depends on how much stuff you use. When we express a delta H for a reaction, we want that to be a standard value per mole of that reaction. So to turn your Qs into delta H's, you have to take your amount of heat and divide it by your moles of your limiting reactant. And that then will be a standard value. The other thing you have to recognize is when you're measuring your change in temperature, you're measuring the change in temperature of the surroundings. So the first Q that you get initially is the Q of your surroundings, which is always opposite to the Q of the reaction or your system. So like if your temperature of your surroundings is going up, that means that the surroundings was absorbing energy from the system. So the reaction must have been releasing heat. So if you get a positive Q of your surroundings, that means you have a negative Q of your system or your reaction. And the opposite is also true. If your surroundings is getting colder, that means it's losing heat. It's negative Q. Where is that heat going? It's going into the reaction. So in that case, the reaction would have a positive Q. So when you're looking at heats of reaction in calorimetry, you have to pay attention to this sign convention here. And then you have to divide whatever your Q of your reaction is by your moles of your limiting reactant to turn this into a delta H of your reaction. Okay, so that's one method of measuring a heat of a reaction is by measuring it in the lab. Another way to get the delta H of the reaction is to take the sum of the moles of the heats of formation of the products minus, oh, I didn't leave enough room, the sum of the heats of formation of your reactants. In other words, how much heat is absorbed or released in the formation of the products versus how much heat is absorbed or released in the formation of the reactants. That delta is how much heat you're going to get out of that reaction or how much heat you're going to need to put into that reaction. And heats of formation are standard values. And remember, heats of formation of elements in their standard states is equal to 0. Because those were formed during the Big Bang, there's no energy needed to form the elements. Whatever we've got, we've got. Okay, so those would be values that you would look up in a book or they'd be given in the problem. Another way to get a delta H of a reaction is to take the bond enthalpies. Now, the symbol for bond enthalpy is D. I just don't use it very often. So anyway, the bond enthalpies of the bonds that are broken minus the bond enthalpies of the bonds that are formed in the reaction. And this one is backwards from this one. Like this one is products minus reactants, bonds broken minus bonds formed. The bonds that are broken in the reaction are the reactant bonds, and the bonds that are formed in the reaction are the product bonds. And again, bond enthalpies are standard values. It's how much energy do you need to put in order to break apart a bond. So bonds broken minus bonds formed. And here, when you're doing this equation, you guys, remember, you got to draw your Lewis structures. Because like, for example, if one of your reactants is methane, you're breaking apart 4 carbon-hydrogen bonds, right? So you actually have to like count up how many of each bond is being broken in your reactants versus how many bonds would be broken in your products. Now I get it, like you're not breaking apart product bonds, but it's just this comparison of like, okay, if I needed to break apart all the bonds of the reactants, and if I needed to break apart all the bonds of the products, the delta between those is your heat of reaction. I understand that we're not breaking apart product bonds, we're forming product bonds, but that's just the calculation. It's just this comparison between these bond enthalpies. It's really just a comparison of the stability of the reactants versus the stability of the products. And remember, bond enthalpies, these Ds, these bond enthalpies, D stands for bond enthalpy. These are always positive values. You have to put energy in to break a bond. These are positive values. Okay, so we've got the lab. We have these 2 standard sets of values that we can use. And then we also have Hess's law. Which is when we've got a series of reactions that we can add up in order to result in an overall reaction. Like let's say you have a reaction that just takes a super long period of time or releases a ton of energy and just isn't feasible to do in a calorimeter. You can take smaller reactions that you can actually measure and sum them up. And when you add up the reactions, you add up your delta H's. So just remember with Hess's law that there's different manipulations of delta H. Okay, so like if you multiply your reaction through by a coefficient, so like if you multiply through your reaction by 2, you would have to multiply the delta H by 2. And if you reverse your reaction, you're going to change your sign of your delta H. So just remember, if you multiply through by a coefficient, multiply your delta H. If you reverse your reaction, you flip your sign. And then when you go to add up all of these things together, you know, you add delta H of one reaction to the delta H of the other reaction to get the delta H of the overall reaction. So you sum or you add your delta H's. These manipulations are very different when we're manipulating K, our equilibrium constant, which we'll talk about on Friday. All right, I'm going to pause there because that was pretty fast and furious before we go into calorimetry. Any questions on like the 4 different methods? Lab, heats of formation, bond enthalpies, or Hess's law. These are all different ways to just figure out how much heat are we going to get out of a reaction. Is it going to be endo or is it going to be exo? And what is the magnitude of that delta? Any questions there? Let's make sure I talked about everything I want to talk about before we go into calorimetry in detail. Okay, let's do calorimetry. So the type of calorimetry that we looked at, there's 2 different types of calorimetry. There's coffee cup calorimetry, which is what we did in the lab. And then there's this other type called bomb calorimetry, which we did not do. We don't have a bomb calorimeter at the high school, but you'll probably have them in your college level labs. If you need to measure heats of combustion reactions, right, we couldn't do that in a coffee cup. We would like burn up our coffee cups. So, you know, reactions that release a lot of heat are typically done in bomb calorimeters, which are the bomb calorimeters are at constant volume. And so pressure changes, like it's a rigid sided container. So bomb calorimetry is often called constant volume calorimetry. And coffee cup calorimetry is sometimes referred to as constant pressure calorimetry because these stay at atmospheric pressure the whole time because the cup can expand and contract. Anyway, but really we're going to focus on coffee cup calorimetry. So this is the setup. You guys know, usually these reactions are taking place in solution. And we measure the temperature change of the surroundings. Okay, so we measure the delta T of the surroundings. And so if we want to figure out how much heat was transferred between the system and the surroundings, we're going to use the mass of the surroundings, which is typically the mass of the water or the total mass of the solution, the specific heat of the surroundings, which again, if it's water, it's 4.18, and the delta T of the surroundings. Okay, so obviously we have measured the Q of the surroundings. So if this temperature goes up, if we get an increase in temperature here, just for this particular example, if we get an increase in temperature of the surroundings, final minus initial is going to yield a positive delta T, and thus a positive Q of the surroundings, which means that this reaction that was taking place, this system, was exothermic, negative Q of the system. The system, of course, being the reaction. So this particular diagram was representing an exothermic reaction. If we had the opposite thing take place, like let's say that the temperature dropped, right? So I'll use a different color here. If the temperature went down, so Q equals MC delta T, we would end up with a negative delta T and a negative Q of my surroundings. So if the surroundings was losing heat, that must mean that the system or the reaction was absorbing heat. So you'd have a positive Q for your reaction. Oh, I just wrote surroundings twice. Whoopsies, I meant system. Positive Q of your system, which is your reaction. And this scenario would be an endothermic reaction. The water is getting colder because the heat that that water has is going into breaking apart those bonds in that endothermic reaction. And then, of course, for both of these examples, no matter what type of Q you are working with, positive or negative, to turn this Q into a delta H, you would take your total amount of heat, you would take your Q total, and you would divide that by the moles of your limiting reactant. And now you have your delta H of your reaction. I don't remember. I did these problems a long time ago. I'm trying to think if one of these problems, I think one of the FRQs on the website is a calorimetry problem. Any questions there? Okay. Oh, there's Rosa. Hi, Rosa. We're reviewing Thermo. Okay, so I've been saying over and over again, like reaction, 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 but not just reactions. Like there are delta H's associated with things going into solution, right? There's delta H's of, why did I just write two deltas? Goodness. There's delta H's of solution, which of course we know is just a physical process, but we can get absorption and release of heat when things go into and out of solution. For example, remember that hot ice demo I did with like the supersaturated sodium acetate? When that sodium acetate precipitates out and crashes out of solution, it's really exothermic. It feels really hot. Maybe that's a demo that you guys could do at home. Ooh, I'll add that to our lab analysis, some at-home fun. So there's delta H's of solution. There are also delta H's involved with phase change. So like how much heat is absorbed when something goes from a liquid to a gas, delta H of vaporization. How much heat is involved when something goes from a solid to a liquid. It's called the delta H of fusion. we know that there's also heats involved in the formation of elements, delta H's of formation. So it's not just reactions, right? Solutions can absorb and release heat, and phase changes can absorb and release heat. So let's take a look at that. I'm not going to spend a ton of time here because we actually looked at this. We were looking at this diagram when we were reviewing, I think when we were reviewing like intermolecular forces. So we've already looked at heating curves in our review sessions. So like I said, let's just talk about it really quickly. Remember, your phase changes are happening on these flat portions of your diagram. So here is where your solid is turning into a liquid. And the amount of heat needed to change a mole of solid ice into a mole of liquid water would be the delta H of fusion. And your phase change from your liquid to your gas is taking place up here at this flat portion, liquid to gas. And this is your delta H of vaporization. That is how much heat is needed to turn a mole of liquid water into a mole of gaseous water. Now, of course, heat is also being added when we're warming up the ice from, from -20 up to 0, the melting point. There's also heat being added when you're warming up the liquid water from 0 degrees Celsius up to the boiling point at 100. And of course, you can also superheat the gas into a plasma. So there is heat being added in these portions of your diagram as well, but the amount of heat being added here and here and here, that is not heat being added to change state. That is heat being added to change temperature. So if we wanted to measure the heat added in those 3 portions of this diagram, we would use Q equals MC delta T. Because here we're not using the temperature to separate the molecules from one another in a phase change. Here, the heat being added is making those molecules just move faster and increase temperature. So if you're trying to figure out heats of vaporization and heats of fusion, you're going to be looking at the amount of heat needed to change state, as opposed to the amount of heat needed to warm something up. Yes?
What does the x-axis on that graph say?
Oh, I think it's heat added. I think it's kilojoules. Sorry, let me scroll down for you. Yeah, or calories. So they did calories instead of joules per gram. Normally on these diagrams, no problem. Thank you for telling me you couldn't see that. Normally on these diagrams, you won't even actually see magnitude values here. Oftentimes you'll just see like reaction progress down here. Sometimes you'll just see heat added. They'll be sometimes they're very generic. This one was a little more detailed. And I think that's all I wanted to talk about. That was easy. Let me double check is it all blank? Yeah, I think that's all I wanted to talk about. Let me check my book one more time. Calorimetry. Phase diagrams, we did that last time when we were talking. I don't think we need to talk phase diagrams again. Yeah, we don't have to talk about entropy or Gibbs. That's it, you guys. All right, so I'm gonna stop recording so you guys can show your lovely faces and tell me how excited you are to be in term 4.